Welcome back to the channel. In the previous video, I've explained which factors are responsible for the physical size of a modern motherboard. In this video, I will analyze the full power sequence of a modern desktop motherboard. The power sequence in the desktop motherboard refers to the precise order and timing in which power is delivered to the motherboard's different components during the startup. Modern desktop motherboards house interconnected components like the CPU, the random access memory and the chipset, each of which depends on others to function correctly. For instance, the chipset or the PCH often needs to be powered before the CPU because it has to facilitate the communication during the initialization. Also, the random access memory must be operational before the CPU can access it for its first instructions. A precise voltage sequence ensures that these dependencies are met, allowing the system to boot successfully. I don't know if the power sequence can be discussed in one video. If not, I will make a multi-part video. By the end of this course, you will be equipped with enough knowledge to analyze and repair any motherboard. If you gained any value from this guide, consider giving it a like and help me to grow the channel and create more content that you enjoy. And do not forget to subscribe to the channel for more in-depth analysis like this one. So, let's start. In this video, I will be analyzing the Z270 Gaming Pro from MSI, which is a 7th generation motherboard. Analyzing this 7th generation motherboard provides a basic understanding of motherboard architecture, component layout, and functionality that can be applied to higher generation motherboards. Understanding the power sequence of the 7th generation motherboard equips you with the framework to anticipate and understand improvements in new generations of motherboards. This knowledge will assist you in troubleshooting different motherboards, and of course there will be little differences in the power sequence with each new generation motherboard and CPU manufacturer, but the basic information still applies. The Intel Z270 is a high-end chipset. It was introduced in early 2017. It was designed to support 6th generation Skylake and 7th generation Kaby Lake Intel Core processors. The Z270 chipset acts like a central communication hub. It helps the different parts of the computer like the CPU, the memory, storage and other devices to talk to each other. Think of the chipset as a traffic controller that directs data where it needs to go inside of the computer. The chipset only works with CPU that the chipset supports. Let's identify the most important components on this Z270 mainboard. This is the CPU and this chip here is the chipset Z270. I have removed the rectangular heatsink that is above this chipset. So normally it looks like this. On the other side, this is the Super I/O chip. This chip is responsible for managing legacy and low-speed input-output functions that are not handled by the CPU or the chipset itself. This is the feedback circuit, also known as the real-time clock circuit. This RTC circuit tracks time and date continuously, even when the system is powered off. It uses a small 3-volt battery to maintain its operation independently of the main power supply. So when there is no mains connected, this battery will provide power to generate a real-time clock signal. This is the 24-pin ATX power connector. This connector is the primary power supply connection that delivers electricity from the power supply to the motherboard. When you turn your motherboard on, the power supply will generate different voltages that the motherboard needs. This is the CPU power connector. On one row it is connected to ground and the other one will get the 12 volt from the power supply. This power connector will deliver the necessary power to the CPU. These connectors typically come in a form of 4 pins or 8 pins. The power supply for the CPU is separate from the 24-pin ATX power connector because this power connector is designed to handle high current and power demands that the CPU needs. In this region there is a voltage regulator that will create 3.3 volts. Near the Super I/O there is a 3.3 voltage regulator that will provide power to the Super I/O. Near the chipset there is a crystal located. This crystal will generate a clock signal of 32 kHz. On the end of the motherboard there is a voltage regulator that will generate 5 volt. Between these two PCIe slots there is a voltage regulator that will create 3 volt standby. In area 12 there is a voltage regulator located that will generate 1 volt for the PCH chip or the chipset. In region 13 there are some voltages generated for the CPU, and these voltages are around 1 volt and is needed by the CPU. VCCST powers the standby logic and parts of the CPU that must remain operational even in low power states like sleep or hibernation. In region 14 you can connect the front panel connectors for the power button. Near the audio IC there is a USB controller. This controller is responsible for generating the voltages and data signals from the different USB ports. This voltage regulator will create the power for the USB at the rear side. So the power for the front side USB connectors is generated in this region. In the region 18, 19, 20 and 22, these voltage regulators will create the power for the DDR RAM memory. There are different voltages that the DDR memory needs, and these regulators will create that voltage. In area 23 and 24, these are CPU voltages. One is called VCC SIO and the other one is called VCC SA. VCC SIO refers to a voltage rail used to power the input and output circuits that are in the CPU. VCC SA stands for Voltage for System Agent. The system agent is a component inside the CPU that is responsible for different tasks like managing the memory controller, PCIe lanes, integrated graphics, and other input-output subsystems. These two voltage rails are also voltage rails for the CPU. In area 25 we can measure an important signal, the PCH Power OK. PCH Power OK is a signal generated by the PCH to inform the CPU and the BIOS that the PCH has been properly powered and fully functional. In area 26 you can find the CPU Power Good signal. The CPU Power Good signal is generated by the VRMs or the controller that powers the CPU. It confirms that the CPU has received stable power, including the correct voltage and current, and it is ready to operate without issues. So the power generation for the CPU V-core is okay, and the signal can be found here. Between these two sockets and also on some dedicated pins on the RAM slots, there is a signal called DRAM reset. When the system is powered on, the DRAM reset active low signal is pulled low to reset the DRAM. This ensures that the memory modules are in a known cleared state before data is read or written. In this area near the Super I/O, there is a signal called platform reset active low. The hash symbol indicates that it is an active low signal, meaning the reset is triggered when the signal is pulled low to ground. So in every signal that has a hash, it means that the signal is active low when it's pulled to ground. In area 29 we can find the CPU reset active low signal. When the CPU reset signal is pulled low, it forces the CPU into a reset state, actively stopping its current operation and clearing any internal states or registers. This ensures that the CPU starts executing from a known state once the reset is deasserted, so the signal goes back high. In area 30 we can find the CPU PWM controller. This controller will drive the VRMs that will generate the V-core for the CPU and the graphics core for the CPU. In area 33 we can find the BIOS IC, and on 34 we can find the BIOS programming pins. With these pins you can flash the BIOS in circuit without removing the BIOS. In area 35 you can find these two pins, and when you short this pin to ground, it will trigger a intruder signal. The intruder signal, sometimes referred to as the intruder detection signal, is used in modern computer motherboards as a part of a security feature to detect physical tampering or unauthorized access to the system. This signal is generated by a detection switch or sensor, which monitors whether the computer case has been opened. In this image, I will explain what the most important components, how they communicate with other components. First, the PCIe 16 data lanes. So in this PCIe slot, you will connect the GPU, and this communication will go between the CPU and this slot. These two slots have one data lane, and these two slots will communicate with the PCH. This PCIe slot has 8 data lanes, and this communicates with the CPU. This slot has 4 data lanes, and this slot will communicate with the PCH. These two M.2 slots will communicate with the PCH. In area 6 are SATA ports, and these SATA ports are communicating with the PCH. On these two connectors you will connect the USB 3.1 ports, and these ports will communicate with the USB controller. These two USB 2.0 ports will communicate with the PCH. The mouse and keyboard will communicate with the Super I/O chip. The image output on this DVI connector comes from the CPU. This USB 3.1 port will communicate with the PCH. In area 12 you can find the LAN interface, and the LAN interface will communicate with the LAN controller, that is this chip. In area 13 you can find the front panel audio connector. This connector communicates with the audio chip. You can connect a fan connector on this connector. The PWM signal that will drive this fan will come from the Super I/O. PWM signal that drives the CPU fan will also come from the Super I/O chip. In area 16, this is the RGB LED microcontroller. So this will drive all the different RGB LEDs that are on the board. And this chip will get its data from the I2C interface. This is the BIOS, and the BIOS is a slave device, and the master is the PCH. And this V-core controller communicates with the CPU. The debug LEDs are located here in area 19, and the debug state of these LEDs is driven by the PCH. The LAN controller itself also communicates with the PCH. The I/O chip also communicates with the PCH. This USB controller that will drive the different USB ports also communicates with the PCH. The PCH or the chipset communicates with the CPU. The CPU itself communicates with the PCH. It will communicate with the random access memory. CPU will communicate with the PCIe slots of 8 data lanes and 16 data lanes. Also, the monitor signal that will go to your monitor comes from the CPU if the CPU supports integrated graphics. This signal will go to the DVI connector or the HDMI connector. The BIOS chip is located in this region. When we zoom in, then this is the BIOS chip. The BIOS is responsible for the post-power on self-test process, where it checks the CPU, the memory and other components to ensure that they are working properly. A malfunction or bug in the BIOS can lead to a failed post, causing the motherboard to appear faulty. If the BIOS fails to initialize certain hardware components like the CPU or RAM, the system will not boot, even if the motherboard and other hardware are functional. And these problems are typically related to how the BIOS interacts with the hardware and software during the system's startup and operation. BIOS corruption is one of the most common reasons of motherboard failures. The BIOS is stored in a non-volatile memory, usually a EEPROM or flash. If the BIOS gets corrupted due to factors like power loss during a BIOS update, interrupted updates or faulty software tools, the system may fail to boot, or the motherboard may stop working entirely. This could render the motherboard unresponsive, as the motherboard cannot communicate with the CPU or other critical components without a working BIOS. Updating the BIOS improperly can result in a corrupted BIOS version, causing the system to be unstable or not boot at all. This is why many motherboards include a dual BIOS system that offers a backup BIOS in case an update goes wrong. Newer hardware components like a new CPU, RAM module or GPU may not be compatible with old versions of the BIOS. If the BIOS does not support the latest hardware properly, the system may fail to recognize components, result in poor performance or fail to boot altogether. Incorrect BIOS settings can lead to hardware instability. These settings may cause the system to crash or fail to boot. For example, manually overclocking the CPU or RAM through the BIOS might result in an unstable configuration that can cause the system to fail. If a user changes the settings like the CPU voltage, memory frequency or power settings, the system might experience instability or even hardware damage. Sometimes a simple reset of the BIOS to default setting can solve these stability issues. It's rare, but the BIOS chip itself can also fail. This can be due to manufacturing defects, overheating, or power surges that damage the chip or its components. When troubleshooting a motherboard, it's essential to work in steps to identify the source of the problem. I began by visually inspecting the motherboard for any signs of physical damage. This includes looking for burned components, swollen or leaking capacitors, or any visible damage to the PCB traces. Even a small crack or scorch mark could indicate a failure point. Next, I ensure that all connections were secure. This includes the power connectors from the PSU, data cables for storage devices and other peripherals. I also reseated the RAM and CPU to ensure that they were properly installed, as loose connection can often cause issues. After confirming the physical integrity of the components, I moved on to testing. I verified the power supply's output using a multimeter to ensure it was providing a stable voltage. A failing PSU can cause erratic behavior or complete failure to boot. From there, I tested each RAM stick individually in different slots to rule out any memory issues. I also double-checked the CPU for signs of bent pins or improper seating, as these are common sources of boot problems. If no issues were found during these checks, the next step would be flashing this BIOS. This chip here is the PCH or the chipset, and the SPI part is used to communicate with the BIOS chip. So these are the pins that will communicate with the BIOS. The PCH is configured as a master device and the BIOS is configured as the slave device. This pin here is the serial clock pin. This pin carries the clock signal generated by the PCH. The output of this clock signal goes from the PCH to the BIOS chip. The IO2 pin is used as a write protect pin, and this signal is active low and prevents unauthorized writing to certain parts of the BIOS chip. The signal goes to the input of the BIOS chip. When the write protect signal is low, the write protection is enabled. The IO3 signal is configured as a hold pin. This signal temporarily pauses the communication to the BIOS chip. This is the MOSI master out slave in pin, and this pin carries data from the PCH to the BIOS chip. The MOSI pin transfers commands and data, like read or write instructions, to the BIOS chip. The MISO pin allows the BIOS chip to send the requested data back to the PCH. So MOSI will send a command read or write instruction to the BIOS, and the BIOS will reply it on the MISO line. When the chip select goes low, it means the BIOS chip is selected to communicate with the PCH. Then the clock signal will start. Every bit transfer happens on a clock edge, either rising or falling depending on the configuration. So on every pulse, a bit is sent. And the same applies when the data is sent back to the PCH. So every bit will be sent on every clock pulse. The chip select pin ensures that only the selected BIOS chip is responding to the commands. When the chip select is low, the BIOS chip is active and data can be read or written. This is the BIOS chip, so this BIOS chip is in a slave configuration, so the PCH is the master and the BIOS chip is the slave. When the PCH wants to communicate with the BIOS chip, it pulls the chip select pin low. This is the chip select pin, it comes from the PCH and it will pull this line low. Next, the PCH will generate a clock signal, and this clock signal will go to this pin, the clock pin. After that, the PCH will send a command, a read or write command, to the BIOS chip. When the BIOS chips want to send the information back, it will send it on the MISO pin back to the PCH. The BIOS chip needs power to operate, it's 3.3 volts. And when you look at the part number, there's a little trick. So if there is no W after the F letter, then you can conclude that this BIOS chip uses the 3.3 volt to operate. When you want to flash firmware to this BIOS chip, there are two options. You can desolder this chip and flash it on a firmware flasher. And you can also program it in circuit with these jumpers. All the signal lines of these jumpers will go to the BIOS chip. So then you can program it in circuit without removing this BIOS chip. And this is how the BIOS circuit looks like on a motherboard. So these are the SPI jumpers, and with these jumpers you can program your BIOS. This is how the BIOS works when the power button is pressed. On power up, the PCH sends clock pulses via the serial clock pin. The PCH sets the chip select pin low to activate the BIOS chip. The PCH sends read or write commands over the MOSI line to the BIOS. The BIOS chip processes the commands and prepares the data. For read operations, the BIOS chip sends the data back to the PCH via the MISO line. For write operations, data is sent from the PCH to the BIOS chip via the MOSI line. Once the data transfer is complete, the PCH sets the chip select pin high, deactivating the BIOS chip. This is how an ATX power supply looks like. An ATX power supply is a type of power supply unit designed to provide electrical power to the desktop computer that follows the ATX form factor standard. The ATX power supply converts the high voltage alternating current from the wall outlet into a lower voltage direct current, so it will convert the AC down to DC. This DC voltage is needed by different components inside of the computer. This connector will deliver the different voltages to the motherboard. The CPU connector is a 4 or 8 pin connector, and this connector will deliver 12 volt to the motherboard. On the motherboard, this 12 volt will be converted into a V-core voltage for the CPU. These are 6 or 8 pin PCIe connectors, and these connectors can be used to power the graphics card, also storage devices, fans, cooling system and other peripherals. When you connect this power supply to the wall outlet and you connect the 24 pin to the motherboard will draw a standby current. The standby current should be between the 100 to 300 milliamps, but it also depends on how many RGB LEDs are turned on in standby mode. So if there are more LEDs, it will draw more current. You can measure the plus 5 volt standby with the multimeter, put the black probe to ground and the red probe to the 5 volt standby pin. The plus volt standby rail in the ATX power supply provides a small amount of power to the motherboard and also to certain components. So even when the computer is turned off or it is in a low state like sleep or hibernation, it will draw a small amount of power. The standby power is needed for enabling specific functions that are required to remain partially powered, even when the main components are off. If you want to see if the power supply generates all the voltage, there is a test that you can do. What you can do is you can connect the PS on pin to ground with a paperclip or wire to check if the power supply turns on and works properly without being connected to the motherboard. So when you jump the PS on to ground, it will generate all those voltages. The PS on pin is used to control whether the power supply is on or off. This pin is located on the 24 pin ATX connector, and by default this pin is 5 volt high. When you jump this pin to ground, this power supply will be turned on and it will start generating all these voltages. The resistance on this PS on pin is very high. This is the 24 pin power connector. On pin 9 you can find the standby voltage of 5 volt. This standby voltage of 5 volt is used on the motherboard for different components, like the Super I/O chip. Most of the time this 5 volt is converted back to 3 volt standby voltage. So there are different components on a motherboard, like a USB high side switch, some controllers, USB-C controllers, some low drop voltage regulators. All those chips needs power in standby mode. When the power supply is turned on pin 14 there will be minus 12 volt created. This voltage of minus 12 volt is used by the audio amplifier. From the 5 volt standby voltage, the standby voltage of 3 volt will be created. This standby voltage of 3 volt is needed to power the Super I/O chip and to generate signals like the power button signal. If the power button signal is missing, the mainboard will not power on. And that is because the 3.3 volt is needed to generate a pulse that will go to the Super I/O chip. Also, the 3 volt standby will be converted into 3 volt SIO, The 3-volt SIO voltage rail on the motherboard stands for a 3-volt south bridge input-output. This rail supplies 3.3 volt to the Super I/O chip. This is the power sequence flow diagram for a 7th generation Intel motherboard. The motherboard power sequence is a series of steps that ensures that the computer powers on safely and initializes all components correctly. In short, the power sequence in a motherboard begins with power detection. When the power supply is connected and turned on, the motherboard detects a stable power source and activates standby power. When you press the power button, it will eventually send a signal to the power supply to start delivering full power to all voltage rails. Once the power supply stabilizes and verifies the voltage levels, it sends a power good signal to the motherboard. This ensures that the power is safe for the system to operate. The motherboard then uses its voltage regulators to adjust the incoming power to correct levels needed for different components, such as the CPU, memory, and the chipset. Next, the motherboard initializes its clock signal, which creates the timing signals required to keep all components working in sync. After this, a reset signal is sent to ensure every part of the system starts from a stable known state. The motherboard firmware BIOS then takes over. It performs a series of checks called the power on self-test to ensure that the critical components like the CPU, RAM, and storage are functioning correctly. After the components pass these checks, they are powered up and initialized one by one in specific order. The process ensures that each part of the system receives the power safely, so the computer can transition to loading the operating system. So what you see here is the power sequence of this Intel board. Every voltage or signal has to be created in the right order. So let's say if the SIO 3 volts is missing, it will not proceed to the next step. This is the sequence for the RTC circuit, and after that we have a standby sequence, followed by a power on sequence. When the motherboard is turned on, eventually these two reset signals has to be released. When these two signals are released, then you have a initialized motherboard. The power sequence is for every motherboard and every different chipset a little bit different. The most important part is to measure the signals that are important for booting the motherboard, like the PCH power OK, the reset signals, power good signals, the sleep modes, the ATX power OK, CPU power good, PCH power good. The most important signal that are on every motherboard is the platform reset signal and the CPU reset signal. These two signals eventually have to go to a high state. The motherboard have different states. The G3 state, also known as a mechanical off state. The system is physically unplugged from the main power source. Only the RTC battery is connected, so the RTC battery will provide power to the RTC circuit. Then we have the S5 state. Every voltage rail or signal at this point has some kind of state. In the S5 state, the system is shut down with no active memory or task, but with standby power maintained for specific wake-up events. One of those events is the power button, so when you press the power button, you want that the motherboard goes into power on state. And this is the power on state, the working state, so the system is fully powered on and operational, all components are actively running. In this state, you know which voltages has to be present and what the signal should be. I will give an in-depth analysis for each sequence. I will start with the first one and I will work it down to the last two signals that are the reset signals. I have analyzed 37 steps, so let's start. In the first power sequence, we have to create the RTC power for the PCH. The ATX power supply is not connected to the power outlet, so we are in G3 state, and G3 state is the mechanical off state, so it is physically only the motherboard with the RTC battery on it. In that case, we have to generate the power for the RTC circuit that comes from the coin cell, the battery, and we have to also create a reset signal that is high. The creation of the RTC power is done in this region. This circuit is part of the RTC circuit. This circuit delivers the RTC power to the chipset or PCH. When the ATX power supply is not connected to the power outlet, then this power, the feedback power, comes from this RTC battery. The RTC battery is a coin cell battery of 3 volts that provides the power to the PCH oscillator circuit even when the computer is turned off or unplugged. When you have your motherboard in your hand and the ATX power supply is not connected, the power for the RTC circuit has to be generated, and this comes from the coin cell battery. When the ATX power supply is connected to the power outlet, then there will be a standby voltage created, and this standby voltage will be converted into 3.3 volts, and the 3.3 volt will be the source for the feedback. The main function of the RTC battery is to keep the clock running and preserve BIOS settings when the computer is powered off. Without the RTC battery, when you power up the system after it has been unplugged, the system might show incorrect time and reset certain settings as it loses the data stored in the RTC chip. When the system is powered down, the RTC battery keeps the PCH oscillator circuit powered on, so the time and system settings are preserved. There are 2 power sources that provide the power to the RTC circuit. The first one is feedback, that is powered from a coin cell battery, and the other source comes from a 3.3 voltage regulator. This provides power when the system is on. When the system is shut down or the ATX power supply is disconnected, the power comes from the battery. This component here is a Schottky diode array. This diode array can be used in power switching to ensure that the real-time clock receives the correct voltage from either the RTC battery or from the standby 3.3 volt voltage regulator. This Schottky diode array has a low voltage drop, and it is used for fast switching between those 2 sources. The configuration of this diode array is also known as a common cathode configuration. The common cathode configuration means that the cathode of these 2 Schottky diodes are shared. One anode is connected to the battery and the other one is connected to the 3.3 standby voltage. The diode connected to this regulator will be forward biased because the anode is connected to the output of the regulator, and this voltage is higher than the cathode voltage of the feedback. The current will flow from the regulator through the diode to the feedback power line. The feedback diode will be reverse biased because the feedback is at a lower voltage, so no current can flow from the battery to the feedback voltage rail. When the system is powered down and the regulator no longer provides power, the voltage at the regulator side, the anode side, drops to 0. The diode connected to the feedback will now become forward biased because the battery voltage is higher than the voltage at the cathode side. The current will now flow from the battery through the diode to the feedback voltage rail, and that will power the PCH oscillator in the PCH chipset. This voltage rail will go from low to high, and it will power the PCH oscillator circuit. This diode array has a low voltage drop of 0.2 or 0.3 volts, which ensures that the voltage reaching the RTC is as close to the source voltage as possible. The Schottky diode array can quickly switch between those 2 sources, ensuring a seamless transition between the battery or the regulator without interrupting the RTC's operation because this voltage is very stable. On most motherboards, this resistor between the coin battery and this diode array is 1 kilo ohms. In power sequence 1, we need to create an RTC power of 3 volts. In standby mode and power on mode, this voltage has to be present, so it has to be around 3 volt high, and the signal is created on the motherboard and will go to the PCH. S5 is a standby mode, so the ATX power supply is connected and the 5 volt standby voltage is created. And S0 is power on, so when you press the power button, the system boots up, and that is the S0 state. On every motherboard you can find a coin cell battery, and near this coin cell battery there is some RTC circuit that will generate the power for the RTC oscillator circuit, and the oscillator circuit is implemented in the PCH. Now we can identify the Schottky diode array that is here. So this diode can switch between the battery voltage or the 3.3 standby voltage that is created by the ATX power supply. In this case, we have disconnected the power supply from the power outlet, so the power can only be generated from the battery. In that case, the battery voltage will go through this Schottky diode array. At the output, this voltage will go to the feedback PCH voltage rail that will go to the PCH. When we look at the first power on sequence, power for the RTC circuit, we are in the G3 state and the signal has to be high because this is low, this is high, and the reset signal also has to go from low to high. So when you have your motherboard in your hand, these two signals should be high because of the coin cell battery, because of this battery. And this resistor here is the 1 kilo ohm resistor. Next, we have to change the state of different reset signals. To go out of a reset state, we have to put the signal from low to high. The hash behind the signal name indicates it's active low, and because it's active low, it's still in a reset state. And the signals has to go in an active state, so from low to high. Also in power sequence 1, we have to create different reset signals. And these reset signals are created from the VBAT PCH voltage rail. If you remember, this VBAT PCH was created from a coin cell battery or the 3.3 standby voltage. When this voltage is present, the secondary RTC reset signal will go high. Then we have the primary RTC reset signal will also go high. And the intruder signal will also go from low to high. On most motherboards, the resistor that is used to create the reset signal is around 20 kilo ohms. Also be aware, if this capacitor is shorted to ground, this signal is missing, so it's in a reset state. If you see this reset signal is low, check all the capacitors, maybe one of those capacitors is shorted to ground. For the intruder signal, most of the time this resistor is 1 mega ohm. The intruder signal with the hash symbol indicates an active low signal, and it's typically used for a tamper detection signal. The purpose of the signal is to alert the system when there has been an unauthorized attempt to access the internal components, such as opening the case or removing a cover. So that will trigger this signal. The most common response is that the system will display a warning or alert message on the screen, indicating that an intruder signal has been detected. The real-time clock reset signal is a control signal used to reset the RTC on a system. The RTC is responsible for maintaining the system's time and date, and even when the system is powered off. What will happen when the real-time clock reset signal is triggered? When the real-time clock reset signal is active low, it resets the RTC, which results in the loss of time and date settings. This is the same as removing the power from the RTC, causing it to revert to its default state, usually by resetting the date and time to a default date of time. This is called a secondary real-time clock reset signal. It's the same as this reset signal. The secondary RTC reset signal can trigger some additional functionality within the PCH. The secondary reset signal is basically the same as the primary RTC reset signal. In power sequence 1, the voltages for these signals will go from low to high. In the standby state or power on state, the voltage of these signals has to be high. These signals are created from the mainboard and it will go to the PCH. The RTC power will eventually go to the PCH. On the standby state and the power on state, this voltage rail has to be high. The PCH receives the RTC power and it will go to the oscillator circuit that will drive the crystal of 32.768 kHz. And it will also provide power to the internal RAM or BIOS where the settings are saved. On the left we have the platform controller hub, the PCH or chipset. At these capacitors and resistors, you can measure the signals. Be aware that these signals will be on different locations depending on the motherboard and manufacturer. But most of the time these capacitors and resistors are located near the PCH chip. In power sequence 2 we have to create a RTC frequency, and the frequency is 32.768 kHz. So this frequency has to be generated. The RTC power, the PCH oscillator circuit and the RTC crystal completes the RTC circuit. The RTC crystal is responsible for providing the oscillation or clock signal to the RTC chip, so in this case the PCH chip. This crystal generates a very precise frequency, usually 32.768 kHz, which the RTC circuit uses to keep track of time. This frequency is divided down by this RTC chip that is located within the PCH chip to maintain the seconds, minutes, hours and days. When the motherboard is powered down, the RTC power keeps this RTC chip powered in this PCH chip, so the time and system settings are preserved. So the frequency of 32.768 kHz has to be always present at this crystal. With an oscilloscope, you can measure the frequency at point 1 or 2. On one side, the waveform is smaller than the other one. In power sequence 2, we have to generate a RTC frequency of 32.76 kHz. In the standby state or in the power on state, this frequency has to be generated all the time. In the PCH, there is a pin called PCH suspend clock pin. The suspend clock pin inside the PCH converts the incoming 32.768 kHz sinus wave clock signal into a square wave. This square wave is used for the timing and synchronization. So it will convert the sinus wave that we see here. So this is a sinus wave. It will convert this waveform into a square wave. The actual conversion from sinus wave to the square waves happens in the PCH chip. When you look at the motherboard, near the PCH chip, there will be a crystal. At the output 1 or 2, you can measure the waveform with an oscillator. Sometimes it's also possible to measure the square wave. These components will be located near the PCH chip. In power sequence 1 and 2, the ATX power supply was not connected to the motherboard. In the power sequence 3, the ATX power supply is connected to the motherboard and also to the power outlet. In that case, the standby voltage of 5V has to be generated by the ATX power supply. The first two sequences, we measured the frequency based on the mechanical off state. Now we have connected the ATX power supply to the motherboard and also to the power outlet. The next power sequences are all related by the standby power sequence. So we have to look at all the signals at the standby state for the RTC circuit and the standby sequence. So every signal at the standby state has to be correct. For the RTC battery, it has to go high. For the reset signal, it has to be high. The ATX power supply should generate 5V standby voltage, so this 5V has to be present. Then we need 3.3V, so the state of every signal or voltage has to be present at this location. And if you measure these voltages on the motherboard or the signal lines, and these signals or voltages are not correct based on this line, then you know you have a problem because your system will not boot. According to the power sequence 3, we need 5V standby voltage from the ATX power supply. 24-pin connector is located here. This is the ATX power supply. It is connected to the motherboard and also to the power outlet. On pin 9, the ATX power supply should generate 5V standby voltage. And this 5V has to go from low to high, and high is 5V. And this voltage will be used by different voltage regulators to create standby voltages for the motherboard. So basically, after the RTC clock circuit is running and the frequency of 32 kHz is created, in the third sequence we have to generate the standby voltage of 5V, and that has to be present. On the motherboard you can find the 24-pin power connector, and on pin 9 the standby voltage of 5V should be present, and the resistance value is higher than 700 ohms. So in the standby state and power on state, this voltage should be present, and it comes from the ATX power supply. When the standby voltage of 5V is created, we can move to the next power on sequence, that is number 4. In step 4, we need to generate 3.3V. In the standby state, 3.3V has to be present. This is the voltage regulator that will create the 3.3V. The 3.3V will be used for the RTC power circuit, so this 3.3V will go to the PCH. From the 5V standby voltage, the 3.3V is created. This is an LDO. It will convert 5V to 3.3V. From the 24-pin ATX connector on pin 9, it will go into this voltage regulator. It will start regulating because the enable signal derives from the 5V standby voltage. It will turn this regulator on. We have an input voltage of 5V, and then it will generate 3.3V. This voltage rail is called 3V dual standby well. And the resistance value on the output is 20 kilo ohms. The 3V dual standby well is a power rail that provides a 3.3V supply to certain components, even when the system is in a low power state or standby mode. This voltage rail ensures that specific circuits, such as those necessary for the wake-up LAN, real-time clock, or other components that remain powered on when the rest of the system is turned off. Voltage for these signal lines comes from the 3.3 volt. So this voltage rail will deliver power to the component that needs to be always turned on. In the standby state, this voltage rail will go from low 0 volts to 3.3 volts, and when it's powered on, it still remains 3.3 volt. This voltage is created on the mainboard. This is the voltage regulator. It will convert 5 volts standby to 3.3 volts. So this voltage rail will go from low to high. This voltage rail will go to the RTC power circuit. This is diode array. We now have a 3.3 volt at input 1 that comes from the voltage regulator. The voltage compared to the battery power is higher. So this diode array will pass the source voltage of 3.3 volt to the PCH. And the connection from the battery will be disconnected. When you want to reset the BIOS, you can remove this battery or jump this jumper. When the 3.3 volt dual standby well is created, the next power sequence will create 3.3 volts that will power the Super I/O chip. When the motherboard is turned on, this voltage rail remains high. This voltage regulator will create 3.3 volts and it will power the Super I/O chip. The voltage rail that this regulator creates is called Super I/O 3 volt auxiliary. This voltage regulator will convert 5 volt that comes from the standby power rail from the ATX power supply. It will convert it to 3.3 volt. This voltage rail is a secondary power source used when the main power supply is unavailable or off. Because when the motherboard is powered on, the Super I/O chip gets its power from the 3.3 volt power on rail instead of this rail. And that's why the letter A is in this voltage rail. A stands for auxiliary voltage or secondary supply. To enable this voltage regulator, there is a signal called RTC reset. This has to be high because it's not in a reset state. When the signal is high, it will create an enable voltage that will turn this voltage regulator on. The resistance of this 3.3 voltage is higher than 3 kilo ohms. For power sequence 5, the voltage 3.3 volt has to be created. In standby state, it will go from 0 volts to 3.3 volts, and in the power on state, it remains 3.3 volt. And this voltage is created on the mainboard. If this voltage is not present, the motherboard will not respond to any event or signals. This is a Super I/O chip. This is the voltage regulator. It will convert the 5 volt standby voltage to 3.3 volts that will power this Super I/O chip. This is the RTC reset line. This has to be high because we are out of a reset state, so there will be a voltage present. It will generate an enable signal. This voltage regulator will turn on. It will create 3.3 volts for this Super I/O chip, and this voltage goes to pin 46 and pin 85. When the Super I/O is powered on, the next sequence will be to generate a D-Power OK signal that will go from the Super I/O chip to the PCH chip. In the standby state, this signal will go from low to high, and in the power on state, it remains high. The PCH D-Power OK signal comes from the SIO chip and it will travel to the PCH chip. But the signal will be created in the SIO chip, and it indicates that all the power it needs is stabilized and okay to use. It will send a signal to inform the PCH that it's working fine. This is a Super I/O chip. On this pin, the Super I/O D-Power OK is generated. It will go from low to high. The power supply for the Super I/O chip will also generate this signal line. D-Power OK typically stands for Deep Power OK or Deep Power Well OK. This signal is generated by this Super I/O chip. It's a signal output from the Super I/O chip that indicates a specific power rail has stabilized and it's operational. In power sequence 6, there has to be a voltage created of 3 volts. In the standby state, it goes from low to high, and in the power on state, it remains high, and the signal travels from the Super I/O chip to the PCH chip. So this is the Super I/O chip, and near this chip you have some resistors. At this resistor you can measure the Super I/O D-Power OK signal, and also the D-Power OK signal that comes from the SIO. So this signal will go through this resistor. From here it will go to the PCH, and the signal will go from low to high. This is the PCH, and the SIO D-Power OK signal that comes from the SIO will go into this PCH. When the SIO D-Power OK signal is present, then you can assume that the RTC circuit is working. On this motherboard, you can measure the SIO D-Power OK signal near this diode. On the other motherboards, you have to check the schematics where this signal is present. The next two sequence number 7 and 8, are called sleep suspend and super IO sleep suspend. In the standby state, the first signal has to go from low to high, and the super IO sleep suspend signal will go from high to low. In the power on state, the sleep suspend signal will remain high, and the SIO sleep suspend will remain low. Basically, the super IO sleep suspend is an inverted signal of the sleep suspend signal. This signal comes from the PCH and it goes to the super IO chip, and this signal, the SIO sleep suspend, is generated by the super IO. The two signals can be measured near this super IO chip. The first sleep suspend signal will come from the PCH, it will go through a resistor and into this super IO chip. So the two signals can be measured near this super IO chip. This is the PCH chip. It will output the sleep suspend signal. The SLP stands for sleep and the sus stands for suspend. So the sleep suspend is a power management signal used to indicate that the system is entering a low power state, such as state S3, that is sleep, S4 is hibernate, and S5 is soft off. The PCH or the SIO chip can trigger a reset signal by pulling this signal to low. The sleep suspend signal is a very important signal that comes from the PCH because it can trigger a reset signal. This is super IO chip, this is the resistor, and on one side the signal sleep suspend comes from the PCH and it will go into this super IO chip. This signal has to be around 3 volts. In standby state it will go from low to high, and in the power on state it remains high. And the signal comes from the PCH chip and it will go to this SIO chip. In power sequence 8 is the same signal but it's inverted, so this is the PCH signal, the sleep suspend, this was high, and with this circuit it will be converted to low, and this signal will go into this super IO chip. The signal line super IO sleep suspend is derived from the 5 volt standby voltage. The signal line can be found at a resistor near the SIO chip. The resistance of this signal line is higher than 9 kilo ohms. And if you look at this resistor, the 5 volt will be the power supply to generate this signal, and that's the resistor here. Super IO sleep suspend signal, in a good working standby mode, it should be 0 volt. So in the standby state, it goes from high to low, and in the power on state, it remains low, and the signal comes from the SIO. This signal will create different enable signals for creating the 3.3 volt standby, plus 5 volt, and it will also create the enable signal for the PCH core voltage. If the signal is missing, the motherboard will also not respond to any signals or events. This is a low dropout voltage regulator. It will create a standby voltage of 3.3 volt. This 3.3 volt is created from the 5 volt standby that comes from the ATX power supply, and it can also be created when the ATX power supply is turned on. It will create a VCC 3.3 volt, and this voltage can be the source for this voltage. But the important one is the signal super IO sleep suspend. It goes from high to low. Because it's a low signal, this MOSFET is turned off, and there will be a 3.3 volt enable signal present on the enable pin. The voltage regulator will turn on, and it will generate a 3.3 volt based on the 5 volt standby or the VCC 3.3 volt in a power on state. The important one is that the SIO sleep suspend signal is the signal that will enable this voltage regulator to create 3.3 volt. We need an enable signal to turn this regulator on, and then we have the 3.3 standby voltage. This voltage regulator will create a 3.3 standby voltage, and the super IO sleep suspend signal can be measured here. Also, the super IO sleep suspend signal is used to set the mode for the 5 volt dual power rail. This is a super IO sleep suspend signal. It goes from high to low. It will set the mode for this voltage regulator, and this voltage regulator will generate 5 volt. It's called 5 volt dual because this voltage has to be present on the power on state or in standby mode, so this voltage has to be present all the time. And the source for this power rail can be derived from the 5 volt standby voltage, or when the ATX is powered on, it will get its 5 volt from the 5 VCC pin. Based on this enable signal and also the sleep mode S3 and S4, it will determine what the destination voltage will be. So 5 volt dual can come from the 5 volt VCC or from the 5 volt standby voltage, depending on the mode and those two sleep states. Basically, the Super I/O sleep suspend signal is responsible for determining the destination voltage for this 5 volt dual. So it comes from the 5 volt VCC or the 5 volt standby voltage from the ATX power supply in standby mode. So the Super I/O sleep suspend signal is used to determine which source power rail will be used to generate the 5 volt dual power rail. Also, the Super I/O sleep suspend signal is used to enable the PCH core voltage. So this will create an enable signal called the PCH 1 volt standby enable. And this enable signal will go to a voltage regulator that will create the 1 volt that is used for the PCH chip. With this transistor, the enable signal is created for the 1 volt PCH core voltage. To summarize, the Super I/O sleep suspend signal is an important signal to measure because this signal will be used to generate different enable signals that will create different voltages. If the signal is missing, the motherboard will not respond to any events and it will also not boot. When the Super I/O sleep suspend signal goes low, it will generate different voltages. So the next power sequence will be to create the 5 volt dual. 5 volt dual is a 5 volt power rail that is always generated. So the source voltage can come from the ATX power supply from the 5 volt standby pin. And when the ATX power supply is turned on, it can get its 5 volt from the 5 volt VCC pin. In the standby state, this voltage goes from 0 volt to 5 volt. In region 10, here is where the 5 volt dual regulator is located. So this will create the plus 5 volt. Power sequence 9, we have to create a plus 5 volt. And the source voltage can come from the plus 5 volt standby voltage or the 5 volt VCC when the ATX power supply is turned on. In combination with the mode pin and the state 3 and state 5 pin, it determines where the source voltage comes from. So in this case, the SIO sleep suspend pin is low, so this S5 mode will be high. So apparently the sleep S4 signal will be low. Because of this state, the source voltage will be 5 volt standby, and this comes from the 5 volt standby voltage from the ATX. When the sleep S3 state and the sleep S4 state is high, it will get its source voltage from the 5 volt VCC, and that will be generated when the power supply is turned on. The output of this 5 volt dual power rail is higher than 9 kilo ohms. This is the voltage regulator that determines where the source voltage comes from, but eventually at the output we have to have plus 5 volt. The Super I/O sleep suspend signal has created 5 volt dual voltage rail, and now the Super I/O sleep suspend signal will create the 3 volt standby voltage. So this 3 volt standby voltage will be a voltage of 3.3 volt. This is the standby state, and the 5 volt dual is now high, so this is 5 volt. And next the 3.3 volt has to go high, so it has to be 3.3 volt in the standby state. And when it's fully powered on, these voltages are still present. Between these two PCIe slots, the voltage regulator is located that will create the standby voltage of plus 3.3 volts. In power sequence 10, we have to create the 3.3 standby voltage. This voltage comes from two sources. One is from the 5 volt dual power rail that we created in the previous sequence. And when the ATX power supply is turned on, it will get its 3.3 volt from the VCC 3 pin. The SIO sleep suspend signal that we created in the previous power sequence is low, and because it's low, this MOSFET is turned off. And then the enable signal will be present at this location, and it will be the input for this voltage regulator. When the enable voltage is present, it will turn this voltage regulator on and it will create the 3V standby voltage. If this voltage is missing, what you can do is you can jump the pin PS on from the ATX power supply to ground. It will force the ATX power supply to generate the power on voltages. Then this 3.3V will be available and the 3.3V standby voltage will be present. And if the motherboard is working after that, then you can conclude that the standby voltage of the 5V dual is missing or something in this circuit. In standby mode, this voltage goes from low to high to the 3.3V, and in the power on state, it's still high at 3.3V. This is the voltage regulator chip that will create a 3.3 standby voltage. The resistance on the output is higher than 500 ohms. And this chip is located between those two PCIe slots. When the standby voltage of 3.3V is present, it is used to enable the PCH core voltage. Because the 3.3 standby voltage is present here, it will short this voltage rail, so the gate has no voltage. Because of that, the enable signal that will create the core voltage for the PCH will be high. When the standby voltage of 3.3V is missing, this enable signal will be shorted to ground. On these two transistors, you can find the PCH 1V enable signal. When the standby voltage of 3.3V is created, the next sequence is to create the 1.8V. I could not find this voltage rail on the motherboard, so I will skip this one. But the next power sequence is number 11. And in this power sequence, we're gonna create the 1V core voltage for the PCH chip. So in the standby state, this PCH voltage has to go from 0V to 1V. This is a PCH chip, and near this chip there's a voltage regulator that will create the core voltage of 1V that will be used by the PCH. The voltage regulator is located in region 12. So in power sequence 11, we're gonna create the 1V that will be used by the PCH chip. This is a buck boost converter, and this converter will use the 5V to generate the 1V. The PCH 1V enable comes into pin 7 and it will turn this chip on, and this enable voltage is derived from the 3.3 standby voltage. As you can see here, standby voltage of 3.3V is used to create this enable signal. And this enable signal will turn on this buck boost converter to generate the 1V PCH core voltage. The output resistance is higher than 30 ohms. So to summarize, we have to create 1V. In the standby state, it will go from 0V to 1V, and in the power on state, it remains high. The signal is created on the mainboard and it will go to the PCH. Power supply for this chip comes from the 5V, so this 5V can be the 5V standby voltage, and from the ATX power supply when the power supply is turned on. So this is the PWM controller, also known as the buck boost converter. It will drive the high side and the low side MOSFET, and at the output you can find the 1V for the PCH chip. When the PCH chip is up and running, the next power sequence is the VCCST PLL. This is a CPU voltage, and in the standby state it remains low. So there has to be 0V at the voltage rail that will go to the CPU. Also, the power good signal from the VCCST power regulator remains low. Basically, this voltage rail that will go to the CPU and the power good signal will go high once the system is powered up. But in this case, we're still in the standby state, it remains low. This is CPU, and near the CPU there is a voltage regulator that will create the VCCST voltage rail that will go to the CPU. Also, the power good signal will go to the CPU. This is the voltage regulator that will create the 1V for the CPU. The power supply for this voltage regulator comes from the 5V dual voltage rail, and that derives from the 5V standby voltage from the ATX power supply or the 5 VCC pin from the power supply when it's turned on. When you turn on your motherboard, these signal the sleep state 4 and sleep state 3 will go high. That will create this enable signal. Then the voltage regulator will start generating the 1V for the VCCST, and that will go to the CPU. The output resistance of the VCCST voltage rail is higher than 200 ohms. The VCCST voltage is created from the 3.3 standby voltage. The VCCST is a power rail that serves the standby logic and certain supporting circuits within the CPU. It also powers the PLL section of the CPU, and PLL is also known as a phase-locked loop. A PLL is a component in the CPU that generates high-frequency clock signals used to synchronizing operations across the processor cores and other components. This is CPU, this is the voltage regulator. The input voltage is 3.3 standby voltage, and eventually, depending on the sleep states 4 and 3, it will turn on or off this enable signal. When this enable signal is present, it will generate the VCCST CPU voltage of 1 volt, and that will go to the CPU. The VCCST Power Good is a power good signal that is used in the CPU to indicate the readiness and stability of this VCCST power rail. The resistance on this line is higher than 2 kilo ohms. The VCCST Power Good signal is 1 volt. In the standby mode, this signal is not present, and when you power on your motherboard, the signal will go from 0 volts to 1 volts. The signal is created on the main board and it will go to the CPU. Near this voltage regulator, this power good signal will be created, the VCCST Power Good of 1 volt, and that will go to the CPU. The reset master signal is the last signal that is needed in this standby sequence. A high reset master signal means that the system is stable and no reset or resume operations are currently happening. So basically the system is waiting for an event to trigger a transition from the standby state to an active or awake state. So it is waiting for an event like the power button or the reset button that has to be pressed. So for now, this process is finished, and when this signal is high, so this is the last signal, then you can assume that all the previous voltage rails are okay, and now it's just waiting for an event. The reset master signal can be found at the Super I/O chip at pin 101, and the signal will go to the PCH. In the standby sequence number 14, this reset master signal has to go from 0 volts to 3 volts. And the signal can be found at the Super I/O chip at pin 101. So there's a pin called reset master active low. This signal is an active low signal indicated by the hash suffix, and the signal is generated by the Super I/O chip. The primary purpose of this reset master signal is to perform a system reset during different power states. Basically, in standby sequence 14, this signal has to go from 0 volts to 3 volts. So in the standby state, it goes from 0 volts to 3 volts, and in the power on state, it remains high. And the signal comes from the Super I/O chip and it will go to the PCH. This is a Super I/O chip. At pin 101, you can find the reset master signal. So it has to go from 0 volts to 3 volts. This reset master signal comes from the Super I/O chip and it will go to the PCH. The voltage for this reset master signal is created from the 3 volt standby voltage. These resistors are called pull-up resistors. So the voltage for the reset master signal is created here, and it is about 3.3 volts. When the system wants to reset, it will pull this line low, it will create a pulse, and this pulse will go to the PCH, and the PCH will start a reset process. If you can identify the PCH, you see a lot of resistors near this PCH, and one of those resistors is where you can find the reset master signal. When you want to troubleshoot a motherboard, you can measure all those power rails and signals. But most of the time you can just jump to the most important signals like the resume master signal. If the signal is high, you can conclude that all the previous voltage rails are present, because if there is a voltage rail missing, this signal will not be generated. Let's say, for example, that the 5 volt is missing, then the voltages that are created till the 5 volt are present, and after the 5 volt power rail, all those voltages are not present. Then you can conclude that there is something wrong with the 5 volt power rail, and then you can focus on this power rail. So there can be a short present at this voltage regulator, maybe an enable signal is missing, maybe some components are damaged, but this is how you can troubleshoot any motherboard. Just go to all the power sequences and check if these voltages are present. So basically this is it. These are the most important standby power on sequences, and the system is now waiting for an event and that event is pressing the power button, and that will be discussed in the next video about the power on sequences. In this video I have explained how the standby voltages on the motherboard must be created in the correct sequence to get a stable standby state. In the standby state, the motherboard is waiting for an event to trigger the power on sequence. So basically the motherboard is now waiting for an event to continue the power on sequence. This event, which the motherboard is waiting on, is pressing the power button. When you press the power button, it will create a pulse, and this pulse is the start of the power on sequence. In the next video I will explain what will happen when you press the power button, which voltages and signals needs to be created in which sequence. If you gained any value from this video, consider giving it a like. It will help me to grow the channel and create more content that you enjoy. And do not forget to subscribe to the channel for more in-depth analysis like this one. So till next time, bye bye.